Hi everyone, my name is Hibaseo. Today I'm going to be presenting USBFuzz, a framework for fuzzing USB drivers by device emulation by Hui Peng from Purdue University and Matthias Payer from EPFL. So first we're going to be talking about just going through what we're going to be talking about in today's presentation. We're first going to be talking about the risks that USBs pose, along with fuzzing, what it is, and then with the USBFuzz, which is the project that this presentation is presenting, and then the different components of USBFuzz and how it really works. We're then going to talk about the testing approach, and then we're going to talk about the bugs that were found. And then near the end, we're going to talk about how the USBFuzz can be extended to different OSs. And then we're going to do a comparison with syscaller, which is a competitor for USBFuzz. And then lastly, we're going to talk about some caveats of USBFuzz. And yeah, moving on to first, we're going to talk about some of the USB security risks. So the Universal Serial Bus, which stands for USB, is found in a lot of different technologies. It connects a wide range of external devices to host systems. However, this convenience can also come with some security risks due to the fact that the OS kernel and device drivers were made under the assumption that they could trust these connected devices. And so we can see that there are three main types of USB-based attacks. We can first see that there are attacks on implicit trust. So this is when a malicious device can be seen as trusted, and this can lead to data breaches or unauthorized system control. The next is electrical attacks, and so this is when it exploits the physical design flaws of the USB port, and this can potentially cause hardware damage. And then lastly, we can see attacks on software vulnerabilities, and this is exploiting flaws in the host operating system's USB drivers, and they can execute arbitrary code that they input or cause system crashes. And so we're going to get into what fuzzers are in the next slide, but current fuzzers are not working or not geared towards finding these flaws in drivers of kind of peripheral devices, and it can lead USB drivers particularly vulnerable. And so USBs operate on a master-slave architecture, which divides into a single host and potentially many devices. As the device acts like the slave, it implements its own functionality, while the host side acts as the master and it manages all the devices connected to it. And this architecture allows a single host to manage different types of devices efficiently. And all data communication in the USB must be initiated by the host, and devices aren't allowed to transmit data unless the host requests it. And so the USB standard defines different set of requests that every USB device must respond to. And so this leads to ensuring consistent behavior across the different devices. The host side also has a layered architecture with a hardware-based host controller, and this provides physical interfaces and supports multiplexing device access. And the host controller driver also provides a hardware-independent abstraction layer for accessing these physical interfaces. And on top of the host controller lies the USB core layer, which is responsible for selecting the appropriate drivers for connected devices and managing core routines to allow communication with USB devices. And so the user space programs interact with USB devices using the APIs provided by the kernel subsystems. And the USB drivers typically include a probe routine to initialize the driver and function routines to interface with other subsystems, and this along with other procedures to deregister the driver when the device is unplugged. And so the current USB fuzzers kind of really focus on the probe routines, and so these are automatically started when a device is plugged in. But this leaves other critical areas like the function routines not really tested. And so this has been seen as a significant security risk. And this can lead to the attacks that we just talked about of implicit trust, electrical vulnerabilities, and software exploits. And to really address these gaps and being able to find these vulnerabilities, the research team for this paper decided to build a USB fuzzer that can be used in different environments to kind of find these different to be able to target these different routines or functions. And so I just wanted to bring this up to kind of give a baseline of the importance of the USB security risk. And just in a second, we're going to go into fuzzing, and why this is so important, and then the solution that this paper really presents. So going on to what actually fuzzing is. So fuzzing is a dynamic software testing technique, and this has the goal of uncovering security vulnerabilities by automatically generating random or different inputs and feeding them to the software. And so the goal is to identify unexpected behaviors such as crashes, memory leaks, or code execution paths that could be exploited. And fuzzing is especially effective because it can uncover edge cases, bugs that traditional testing methods might miss. And so the core idea behind fuzzing is to test the system's ability of robustness by overwhelming with unexpected or random data. And so this process can help to identify how well the software handles inputs that are different from what developers expect. So in the security context, fuzzing is really important because many exploits arise from unexpected inputs. It can also be from buffer overflows or other data-related issues. And so additionally, fuzzing USB devices drivers is a unique challenge due to the fact that it involves crossing the hardware and software boundary. And so this means that delivering fuzz data in a way to the USB stack, drivers, and kernel is a hard process to kind of get right. And so the hardware software barrier really complicates things because USB data flows through multiple layers from the physical connection to the kernel space, and each layer interprets data differently, which makes it difficult to target specific vulnerabilities without interfering with other system components. And additionally, the need to emulate hardware behavior adds another layer of complexity. And so due to these different challenges with fuzzing, USBFuzz that we're just going to see in a moment is able to help bridge these gaps between the software and hardware requirements that are found to really be effective in finding vulnerabilities for this edge case that we have of USB devices. And so the approach that USBFuzz really takes allows a comprehensive testing of USB drivers and the related kernel components that we've kind of just gone through, without relying on the actual hardware. And this makes fuzzing more accessible and effective. And so now we can finally go through what USBFuzz, which is the proposal that this paper puts through, and showing just how effective USBFuzz is throughout this paper. So USBFuzz was developed to address kind of these specific challenges we've gone through with fuzzing USB device drivers. And so the framework that this paper presents is designed to overcome the hardware/software boundary and enable security researchers to identify vulnerabilities within the USB stacks and the drivers more effectively. And unlike traditional fuzzers that operate solely on the software level, USBFuzz uses a device emulation to simulate USB hardware and delivers fuzz data in a realistic manner. And so the exact problem USBFuzz aims to solve is a lack of effective scalable methods for fuzzing USB drivers. So existing fuzzers like size caller primarily target system call interfaces, which do not fully capture the complexities of the USB drive device communication. And so USBFuzz fills this gap by providing a modular, flexible platform that allows researchers to test USB drivers in different environments without having extensive hardware dependencies. And it does this through emulation. And so one key differentiator of USBFuzz is its ability to support both broad and focused fuzzing strategies. So broad fuzzing targets the entire USB system, including a wide range of drivers and kernel components. And this approach is ideal for discovering systemic vulnerabilities that affect multiple device types. On the other hand, the focused fuzzing concentrates on specific drivers or device classes, such as webcams, and this can enable a lot of in-depth analysis of the particular components of the USB stack. And so USBFuzz's design emphasizes portability and flexibility, and so the framework can easily be adapted to different operating systems and USB environments, making it really suitable for testing a variety of kernels and drivers. And it supports both coverage-guided and dumb fuzzing as well, which allows researchers to choose the most appropriate technique based on their goals and the target system. And so ultimately, USBFuzz is able to show an advancement in the current fuzzing that we've been able to see so far in the USB space. And it's due to being able to use VMs and by being able to allow these advanced fuzzing techniques to kind of find different vulnerabilities that weren't able to be found before. And we can kind of go through next what the different components are of USBFuzz that make it so unique. And so the USBFuzz is made up of these 6 different components. It's made up of a fuzzer, a guest system, a target kernel, a fuzzing device, communication device, as well as a user mode agent. So the fuzzer is the core engine that generates the random inputs that's going to be used to test the USB drivers. It uses sophisticated algorithms, including coverage-guided techniques, to maximize the exploitation of code paths and uncover hidden vulnerabilities. And the fuzzer continuously mutates input data based on the feedback it receives from the system under test, and allows us to focus on areas that are more likely to contain bugs. And so this iterative process makes it highly effective in identifying the unknown and the known system vulnerable security flaws. Next is the guest system, and it acts as a virtual environment where target operating system and the USB drivers are run. It creates an isolated sandbox that mirrors real-world environments, enabling full testing without risking the stability or security of the host machine. And by using these virtualization technologies, the guest system can easily be reset or reconfigured between tests, which allows a clean slate for each fuzzing iteration. It can help enhance the accuracy of the result as well. And then we have the target kernel, as this component is the specific OS kernel being tested, which includes the USB stack, device drivers, and the other relevant kernel modules. And the target kernel is where potential vulnerabilities are exposed when subjected to these unexpected USB inputs that are generated by the fuzzer. And so USBFuzz interacts directly with the target kernel to monitor its behavior, to identify when crashes happen, and detect abnormal responses that may indicate security flaws, such as memory corruption or higher elevation of privileges that can be a vulnerability. And then we have fuzzing devices. So the fuzzing device is an emulated USB device within the virtual environment. It acts as a stand-in for real hardware, which enables delivery of fuzzer-generated inputs to the target kernel. It simulates different types of USB devices, such as storage devices, webcams, or network adapters, and the fuzzing device helps uncover vulnerabilities across a broad range of drivers. And this approach eliminates the need for physical hardware, which makes the fuzzing process way more cost-effective and scalable, since you don't have to take the time to kind of take in and out USBs as well, since that can be very time and economically inefficient. And next we have the communication device. And so this device acts as the bridge between the fuzzer, which is running on the host machine, and the guest system. And it facilitates real-time data exchange, which is including the transmission of test inputs, the collection of execution feedback, and the synchronization of the coverage information. And so the communication device is really important for maintaining the efficient, low latency interactions during the fuzzing process, which enables the fuzzer to quickly adapt the different strategies it's using based on the responses it gets from the target kernel. Another component that we're going to go through now is the user mode agent. The user mode agent operates within the guest system, and it plays a critical role in monitoring the status of the fuzzing process. It tracks system logs, it detects crashes, and captures error messages generated during the test execution. Additionally, the user mode agent communicates this information back to the fuzzer, which allows for rapid identification and analysis of the discovered bugs. And it can also automate the recovery actions, such as restarting the guest system after a crash. And so this can help speed up the testing process by making sure that we have continuous testing without needing manual intervention to reset the system and kind of take that time to go through again. And so next we're going to now talk about the actual testing approach now that we understand how the USBFuzz has kind of come together. And so the testing approach has been, they set up the hardware and the software environments by preparing the guest OS images. They create initial seed data for the fuzzing process. And then USBFuzz was run on 9 different versions of the Linux kernel, with each version fuzzed using 4 parallel instances over a span of around 4 weeks. And so the extensive fuzzing led to the discovery of 47 bugs, which shows just how effective the USBFuzz could be. And the bugs identified were disclosed to the respective maintainers, and patches were then issued to address all the discovered vulnerabilities. And this shows kind of the real-world nature and the importance of USBFuzz. And so this disclosure also highlights the role of fuzzing and not just identifying bugs, but also how it improves the security ecosystem through this collaboration that's been really launched and seen. And then SizeColor, which is a well-known fuzzing tool, was also used throughout this process as just as a comparison tool, and it found that it outperformed USBFuzz. And we're going to go into more in some later slides about the comparison between these two products and how they really compared. But SizeColor was kind of known to maximize code coverage, and it had more due to its more sophisticated input generation strategies. However, size caller can miss vulnerabilities that occur outside standard compliant areas or the predefined input paths. And so USBFuzz can kind of complement this by feeding data into unmodified systems, what allows us to trigger broader classes of bugs, different types of bugs more. Um, and so USBFuzz really excelled in Linux environments, but the fuzzing of macOS and Windows kind of has some challenges due to the lack of support infrastructure found in these two OS environments. But USBFuzz was able to overcome those challenges, and it was able to find 3 bugs in macOS. And it was also able to find 4 bugs on Windows, which shows that's able to be used in different platforms and it's not platform dependent. And now moving on to what exactly were the bugs that were found through USBFuzz throughout those 4 weeks. So through a lot of testing, USBFuzz was able to uncover 47 unique bugs, and so 16 of these were memory bugs with high security risks in Linux subsystems. 3 of them were critical bugs in macOS. 4 bugs caused blue screen deaths on Windows 8 and Windows 10. 1 of the bugs was on the Linux USB host controller driver, and 1 bug was in the USB camera driver. And so 36 bugs were detected by Kazan, which are serious and can be used to launch attacks. And the other 11 bugs are caused by the execution of potentially dangerous statements. And these can represent potentially dangerous statements, and they can represent unexpected kernel states, which developers can be aware of but don't know how to handle. And the research team that worked on this paper worked with the Linux and Android security teams to disclose and fix all of these discovered bugs. And they first focused on fixing the memory bugs. And so kind of these findings really show the effectiveness of USBFuzz in helping identify critical vulnerabilities. And next, we're going to talk about how fuzzing can be used beyond these 3 OSs that we mentioned. So USBFuzz's versatility kind of goes beyond USB, and it kind of makes it adaptable to other interfaces supported by QEMU. And to use USB in different environments, the process begins with first identifying the target interface, whether it's for network devices, storage controllers, or other interfaces. And then researchers can then implement a fuzzing device specific to that interface and ensure compatibility with the protocols and data structures involved. And so once the fuzzing device is in place, the fuzzer adapts to generate the relevant input data tailored to the new interface. And this step involves adjusting the input models, the mutation strategies, and you can also control the mechanisms to kind of align with the specific requirements of the target environment you're choosing. And the user mode agent can also be modified to detect test completions and accurately monitor the system responses, which can allow comprehensive feedback for all the fuzzing iterations that you go through. And then researchers can also integrate the adapted components into the USBFuzz framework, and it's going to allow iterative testing and refining configurations based on the observed behavior. And so this really allows USBFuzz to maintain its effectiveness across many environments. And this then allows it to help give security assessments for different environments and go kind of beyond the traditional USB peripherals. And so now we're going to go through the comparison between USBFuzzer and SkyScaler. As you can see here, these are 2 graphs or tables that were kind of in the paper about the comparison between code coverage between SkyScaler and USBFuzz. And as we can see, when compared to SkyScaler, USBFuzz doesn't do as well in code coverage. However, USB does have some significant advantage due to the fact that it had greater flexibility and portability. It had the ability to fuzz a broader range of drivers, also able to enhance code coverage in certain situations. However, SizeColor did have certain strengths, which was that it has a more mature ecosystem. It has a well-maintained and extensive ecosystem, and that allowed it to be a more preferred choice for many kernel developers and security researchers. It also excels in coverage-guided fuzzing, so you can use really sophisticated techniques to maximize code coverage efficiently. And SizeColor also has strong community support and has continuous updates and documentation and active discussions around kind of the progress of SizeColor, which USBFuzz currently does not have. And SizeColor is also kind of tightly integrated with certain operating kernels, especially Linux, which allows it to kind of do fuzzing directly at the kernel level. And so ultimately, USBFuzz and SizeColor were found to be complementary tools in the fuzzing ecosystem. USBFuzz's strength are in its broad coverage and is able to detect unconventional bugs, but SizeColor, on the other hand, was able to do a more targeted approach, and it was able to do better deep exploration of specific components. And so leveraging both tools can definitely help enhance the security assessments of USB drivers and their related systems. There are some caveats. So while USBFuzz improves code coverage compared to traditional fuzzers, there are still areas within the complex USB drivers that may remain untested due to limitations in emulation or coverage guided strategies. And so there's also issues with the accuracy of device emulation, which may not perfectly reflect real hardware behavior, which potentially missing hardware-specific bugs. And then there also were some performance overhead, whether running USBFuzz in virtual environments introduces performance overhead, which can affect the speed and efficiency of the fuzzing process compared to direct hardware testing. And USBFuzz also relies on virtualization platforms like QEMU, which may limit its applicability to certain real-time or embedded systems, and that may make it challenging to emulate. But however, despite these caveats, USBFuzz is a really powerful and versatile tool that can really help the security of USBs as a whole and how they are used. The biggest thing is also, like we said before, that there's a lot of industry support for the competition size caller, and so adoption and how USB fuzzer can really truly be implemented is yet to be seen due to the fact that the paper did not kind of walk through an example of USB fuzz being extended to other environments that had already been used in the study. And so we need to see how that really works. And like we kind of mentioned before and gone through in the previous slide, SizeColor did have better code coverage and was able to go more deeper into the Linux and other systems as well. Yeah. And so thank you so much for listening to my presentation today about paper on USB fuzz. And so, and just in conclusion, USBFuzz really shows a significant advancement in USB driver security due to the fact that it has more breadth and is able to kind of fasten the process of making it a cheaper and faster way due to the fact that it does use virtualization. And it was found to be a really modular design. And yeah, if you have any questions, please feel free to reach out to me. My VT email is hibasayed@vt.edu. And yeah, thank you so much.